Welcome to lesson 7.5, Special Types of Linear Systems. So all the linear systems that we've looked at so far, when we solved them, we ended up with an answer written as an XY ordered pair. So what we know that as is a one-solution linear system, meaning if we were to graph it, the lines intersect at a point, and that point is our solution. So we have an x value and a y value, but it's known as one solution because it's written as an ordered pair. Then we have two other main types of linear systems. The second type is a no solution linear system. And no solution occurs when our lines are parallel. So if we look at line A and B here being parallel, never crossing, because they never intersect, there is no solution to this system. So that means the lines would have the same exact slope, but different y-intercepts if we put them in y equals mx plus b. And then our third type of special system is a system with infinite solutions. So we have infinitely many solutions. And this happens when the lines coincide, meaning they are the same line, or they're on the same line, meaning that they would have the same exact equation. If we have two identical equations, our lines coincide meaning lie on top of each other, are the same. So every number along there would be a solution, so we would have infinite solutions because lines go on forever. So, example 1, we have parts A, B, and C that we're looking at for these different types of systems. So, example 1 says solve by any method, state the number of solutions. Now you'll see I did A and B here, parts A and B, just to show you two different approaches. So if we were to use graphing, that means we'd want y equals mx plus b. So if I look at my two equations, negative 2x plus y equals 3, and 4x minus 2y equals negative 6. If I were to solve both those equations for y, the top equation would become y equals 2x plus 3. The bottom equation is also y equals 2x plus 3. So because the same exact equation for both, that means I'd have infinite solutions. But what if we tried a combination or elimination with these two equations? That's part B here. You don't need to do, obviously, both parts in the practice problems, but for your notes, you should have both recorded. So if we tried combinations, with the negative 2x plus y equals 3, we're going to multiply that whole equation by 2, so then we have a negative 4x plus 2y equals 6. Our bottom equation is 4x minus 2y equals negative 6. In this case, when I add my two equations, we end up with 0 equals 0. In that case, if all we have is 0 equals 0, both variables cancel, and the equation is true, meaning 0 is 0, then we have infinite solutions. So if this would end up with like 7 equals 7, infinite solutions. Something equals itself tells us infinite solutions. So if it's an infinite solution combination problem, your x's and y's should both cancel. Then the final equation needs to be true. Let's look at example B. In example B, I used elimination and graphing again. So if we look at the elimination approach, I had to multiply the top equation by 2 and the bottom by 7 to allow my variables to cancel. So the top equation became negative 14x plus 14y equals 14. Bottom equation was 14x minus 14y equals a negative 126. So when we add those two equations, both my variables canceled, so I'm just left with 0 on the left. The right-hand side of the equation became a negative 112. 0 never equals a negative 112, meaning that if both variables cancel and the equation is not true, that system of equations would have no solution. We could find the same by graphing. If we put these both into y equals mx plus b, I don't even need to graph it. I just need to write it in y equals mx plus b to be able to tell what type of solution I'd have. In this case, rearranging the top equation into y equals mx plus b, it would be y equals x plus 1. We had to add the 7x to each side and divide everything by 7. On the bottom equation, to get y alone, we'd subtract 2x and divide everything by the negative 2, so y would equal x plus 9. What I notice here, both equations have a slope of 1, 1x and 1x. They have different y-intercepts. So same slope, different y-intercepts tells me that these lines are parallel. If I have parallel lines, it is a no solution system. And then let's look at example C here. Example C, I only did the combination. And in this case, negative 6x plus 2y equals negative 2, and the bottom equation, negative 4x minus y equals 8, I multiplied the bottom equation by 2 in hopes to cancel out my y's and solve for x. We end up with negative 6x plus 2y equals negative 2, plus a negative 8x minus 2y equals 16. Now, just like our other combination lesson, the y's canceled. Negative 6x plus negative 8x is negative 14x equals negative 2 plus 16 is 14. Divide both sides by the negative 14 and x equals 1. Substitute the x equals 1 back into one of the two original equations. So I put it in the bottom. So negative 4x minus y equals 8. Negative 4 minus y equals 8. So we'd add the 4 to each side. Negative y equals 12. Divide by the negative 1. And y equals a negative 12. So in this case, it was just a normal combination or elimination problem like we've been doing. So it would be a one solution linear system. And our one solution would be 1, negative 12. So no matter which method you use, if it's substitution, graphing, or elimination, either way, you still should be able to arrive at the right answer for if it's a one solution system, a no solution system, or an infinite solutions system.